Well, last but certainly not least, we have Lucciana Caceres, who will be talking about high-resolution spectroscopy of TOI 2109b with GHOST.
Can you hear me? Yeah, right? Okay, awesome. Hi, I'm an undergraduate student from the University of Kansas, and today I'm going to talk about my summer research program that was focused on high-resolution spectroscopy of TOI 2109b with GHOST. Okay. So I think that I'm not going to mention this because already all of you talked about hot Jupiters, but I want to focus on ultra hot Jupiters, and because TOI 2109b is an ultra hot Jupiter. And also I wanted to talk about KELT 9b that you can see up there. I don't think, yeah, here it is. You can barely notice the name, but this is the hottest exoplanet known to date. And I wanted to focus on TOI 2109b because there is a big gap between KELT 9b and WAPS 33b. Because of the temperature of my planet, which I'm gonna focus later on the presentation. I wanted to mention as well some of the chemical components found in ultra-hot Jupiters before, and why are they important? Because we use their characteristics, hot characteristics and different characteristics that they have in their exoatmospheres for us to know more about exoatmospheres in general for all the planets. Now I would like to talk about GHOST and high-resolution spectroscopy. GHOST is an instrument located in La Serena, Chile, in the Gemini South, which is a high-resolution spectrograph having two modes of resolution, a standard resolution and a high resolution. Here I have an example of what is the difference between both of them and the importance in our data. High resolution spectroscopy is very important in this case, just because exoplanets are very dim, as we know, and having high resolution spectroscopy, we can have more specific data of our exoplanet. GHOST has the characteristic of having a wavelength coverage of 383 nanometers to 1,000 nanometers, and also having the capacity of the two modes, the standard and then the high resolution spectroscopy. Oh, wait. Okay. Now I would like to travel to TOI 2109b. We're going to travel 855 light years, and we're going to go to the lead of this project. This planet is 5 times Jupiter masses and 1.3 Jupiter radii. The characteristic of its star is that it's not that different from ours. It has 1.6 solar masses and 1.4 solar radii. And also, as you can see, it rotates its star very quick, and that's 16 hours in total. So that's the shortest period known for a gas giant so far. And I'm gonna play it again just because it's pretty beautiful. So another characteristics of this planet is that it was discovered in 2020, in between May and June, and also this discovery paper was published in 2021. Now I'm gonna focus on our observations. These are some plots of our observations done, having like explanation of air mass variation of 1.46 to 1.72, and also orbit phase coverage of 0.27 to 0.44. We had a number of exposures of 40 and an exposure time of 120 seconds. Now, I'm gonna explain how the reduction process works for this kind of research. Here I have a number of like 5 plots that explain how do we reduce our data. First of all, here we have the observed spectra, which is the first step of Systrom algorithm. We use this algorithm for us to reduce our data and have a total spectrum, well, have the spectrum of our exoplanet. So here we didn't change anything, so this is the raw data. This is the data that we take, and the data that it has not been touched at all. Then we have the normalized spectra, and we use the normalized spectra for later on. Subtracting the telluric and stellar absorption lines. Then we have the first component removal. Here's what Systrom core starts, and it's using the previous parameters that we have from our observations. We take off part of the telluric and stellar absorption lines, and we have some data here that we can see. Here it's the exoplanet atmosphere signal lines, and we are not able to see them, but it's supposed to be like that. So it's supposed to be still hidden, and we use optimal components of removal. This means we use we use the parameters of the planet and the parameters of our observations for us to filter the data, and at the end, having an injection of 100 times the planet signal for us to have these diagonal lines, which I'm gonna explain now. Before that, I would like to talk about petit retrans. Most of people know about it here, but I'm gonna talk a little bit of it. We created models of our planet, models of our planet in different elements for us to focus on the detection of them. So something that is usually done in this type of experiments and this type of research is the Doppler cross correlation. Using, here there was an animation, but I think that you can barely see it from here. But here we have the blue shift and the red shift, and using both of them, we can have the total spectrum of the planet or a cross correlation, which you're later gonna see on some earlier results that they had. Using this, we have
The correct radial
here is
velocity
how,
in the template is exactly
wait,
aligned.
doesn't matter. Okay.
Meaning
Here is how can we cross-correlate the data and how do we get to the detection of the planet or the detection of different elements.
of iron can be drowned out in the photo noise of the star if these lines are.
Okay. As I mentioned before, here is what we have the cross correlation and how do we use it for different detection of different elements. This is another detection done by my PI, my mentor, Emily Diebert here, that it was for a planet WASP 189b. And how do we use it for GHOST? In this case, GHOST has the blue and red camera for different type, like for different wavelength coverage, and also different observation from previous work done. Now, I would like to share my sample results and how do we resulted on this. This is the titanium sample that we had and how do we get to these observations. As you can see here, the absorption lines are way stronger, and that's why we notice here in the red camera. And this is a systemic velocity versus semi-amplitude velocity plot, and that's how we locate the detection of different elements. Also, I wanted to share an iron example, which I'm not going to be able to have time and enough time to explain, but I wanted to talk about how we are going to compare the data of iron with our data and the previous work done before. These are the next steps that I'm planning to do for the future, and because this is an ongoing project, this is all what I want to mention before, and also that we're still working on this project, and we're planning to do our order selection and iron data combination for it. Thank you.
Thank you. Questions for Lucciana?
Thanks for your talk. Over here. Yeah.
Wait.
Oh, sorry.
Oh, there.
Am I going
Okay.
first? Okay. Thanks for your talk. It's really cool that you're filling in this temperature parameter space for the ultra hot Jupiters. I wondered if you could say something a little bit more about the combined iron data
Yeah.
set. Is that an additional data set or?
I'm going to go back and I'm going to explain it. Thank you. I really was waiting for that question. Okay, so this work is not mine. So these two plots here on the left are not my work, and this is my work. This is David Kahn's work done before. This is the detection of iron that he had, and this is the wavelength coverage that he had. Also, the orbital phase coverage that he had. And here, there is a detection of iron, which I wanted to mix with our data and search for a final detection of iron there.
Okay, thanks.
We might have time for one more quick question if there's a quick question. If not, let's thank Lucciana again and all of our speakers from this session.